Hello, my name is Brennan Becerra, and I'll be briefly talking about our project, Time Evolution of Pressureless Euler Poisson Compactness via Projections onto Closed Convex Cones in Hilbert space. So our project was centered around the 1D Euler Poisson system, and we use this to describe the interaction of point masses in a particle model where they're undergoing inelastic collisions and have a gravitational potential. So we were interested in under which conditions the system remains compactly supported in time or remains in some confined interval. And we used Lagrangian formalism for the pressureless Euler system and extended it to the Euler-Poisson case for our purposes. So pressureless Euler is one thing and Euler-Poisson is another. And we used simulations in Python to kind of provide approximations of how the system evolves over time and also just to verify the theoretical results. So our materials and methods, we used projections onto Chebyshev sets in Hilbert space, Lagrangian formulation, and Python modeling. So down here is just kind of a description of how we restated the system to describe it not in terms of like masses at a different location, but with respect to mass, and then so mass instead of location, here's the mass at that location, we say mass and then here's the location in kind of layman's terms. I just want to keep this brief. And we define some piecewise constant maps that relate position, velocity, and acceleration. And you can kind of, here's just some visuals to better see what's going on. So if I have the sum of the masses goes up to 1. So if our mass is between 0.4 and 0.5, this is the representation of the position of that mass. So yeah, in this case, it looks like the masses all have the same mass, as you can see, because they all have this is a uniform partition, but they have different locations. So we have some results related to our projection formulas and also calculating the time at which equilibrium is reached. So x sub t is the projection of the initial position plus t times velocity plus t squared over 2 times the initial acceleration onto the closed convex cone. And this is kind of a generalization of the position of all the masses at a given point in time. And then our other result is just calculating the time at which equilibrium is reached, which is a quite nice result because you can take in the initial conditions of a system and calculate explicitly how long it will take for that to converge to a single delta. And up here is just a simulation of a given initial distribution on a given continuous distribution, not discrete. And this is more or less kind of what it would look like. So you can think like I take a point here, and this is how the point is going to converge in time. And we were able to show under which conditions the compact support remains in the pressureless Euler-Poisson system by projecting the dynamics onto closed convex cones in Hilbert space. We derived explicit weak solutions that demonstrated convergence to a single delta centered at the center of mass. And our simulations were also able to verify these cases. Now, we're still interested in seeing how we could extend this to potentially physical systems, as well as the pressureless Euler-Poisson system with not attractive but repulsive forces. So that's just a brief overview, and thank you for listening.